rational, so we talked about reciprocal graphs. Reciprocal graphs are 1 over a linear graph and 1 over a quadratic. It could be any other ones, but that's all we do in 20-1. Then we're going to talk about rational graphs, which look somewhat like reciprocal graphs. But reciprocal graphs are always 1 over the equation. 1 over the equation, correct? So it has to be a 1 in the numerator and an equation in the denominator, correct? Rational graphs are the same as like a rational equation. Something in the numerator, something in the denominator, correct? You have to have variables in the denominator. So reciprocal graphs are a form of a rational graph. But reciprocal graphs, they have to give you an equation first and say, give me the reciprocal of that. So an example would be, if I gave you like y equals x plus 1, and I told you to find the reciprocal of that. Or let's say f of x equals 1. And then I ask you to find f neg 1x. That's the inverse. Oh my gosh. Just we'll say reciprocal. So they want the reciprocal of it. And we'll say the reciprocal is g of x. So g of x technically is the same as 1 over f of x. So we get 1 over x plus 1. We agree? So a reciprocal function, you have to be given an original function and then ask for the reciprocal, which is 1 over that. Now, what was my non-permissible value for this one? Is x can't equal negative 1. If x equaled negative 1, my denominator would be 0 and we'd have problems. We agree? So that is my vertical asymptote. Vertical asymptote equals the non-permissible value. Because your vertical asymptote is where the graph can't be. So I have a vertical asymptote at x equals negative 1. So remember that meant that at negative 1 I actually had a dashed line, because the dashed line I draw is my vertical asymptote. We agree? For every reciprocal function, what is my horizontal asymptote at? Yes. And for reciprocal functions, my invariant points are at what and what? My invariant points are when y equals what and what? You guys told me this already. Plus or minus 1. So if I want to find the coordinates, I can do it algebraically. Invariant points means they don't change, correct?
Yeah, that's your vertical asymptote.
That's y, not x. Vertical is when x equals negative 1. We're saying there's invariant points when y equals plus or minus 1. They're totally different. One's an x, one's a y. Well, this is at x equals negative 1.
Yeah.
The invariant points happen when y equals negative 1. Like, they're totally different spots, right? So if I want to find invariant points algebraically, I set y equal to 1 and solve, and y equals to negative 1 and solve. So I would go 1 equals x plus 1. Now, why can I use this function and I don't have to use the reciprocal one to get its coordinate? Invariant points means they do not change, correct? So I could use the original equation and solve it, or the reciprocal function and solve it, and I'm going to get the same point, correct? Because the coordinate doesn't change. We agree? So the easier function to use is the original. Because 1 over it will get you the exact same answer, and I'll show you what. So, I set y equal to 1, and now I just solve for the x that goes with it, correct? So we subtract 1, 0 equals x. So I have an invariant point at 0 and 1. And how do I get the other one? I plug -1 in for the y. We agree? So I can plug it into the original again. -1 equals x plus 1. Subtract 1. -2 equals x. So my other invariant point is at -2 and -1. So I'm going to give you an example now and say f of x equals 2x minus 1. I want g of x equals 1 over f of x. So I want the reciprocal function. So my reciprocal function is actually 1 over 2x minus 1. We agree? What is the non-permissible value? Yeah, because we just take this for the non. We take 2x minus 1 and we say it can't equal 0. 2x can't equal 1. X can't equal a half. So where's my vertical asymptote at? 1/2. What's my horizontal asymptote at? For every reciprocal function. Y equals 0, the x-axis. So if I went to sketch this, at x equals, let's pretend that's right in the middle, it's not very good. At x equals a half, I would have a vertical asymptote. And at y equals 0, I would have a horizontal. Where do my invariants happen at? At y equals 1 and y equals -1. Do we have to fill it into the reciprocal or can we fill it into the original? We can fill it into the original or the reciprocal because it's a variant means to say the same. Yeah.
So your variance always be plus minus 1?
Yes, because you're doing 1 over y every single time, right? And the place where y will stay the same if you do 1 over it is at 1, because 1 over 1 is 1, and at -1, because 1 over -1 is -1. So those are the points where we'll always stay the same for reciprocals every single time, because we're doing 1 over y. Because our mapping is xy becomes x comma 1 over y. That's what our mapping is. So all the x values stay the same and all the y's good under 1. And so 1 over 1 is 1, 1 over -1 is -1. So we can use the original function, which is y equals 2x minus 1, and find the corresponding point with that, because if it's invariant, it means it doesn't change on the original, and it'll be the same point on the reciprocal, correct? So if I find it on the original, it actually is the same as the reciprocal. So I'm going to fill in 1 for y. So I'm going to get 1 equals 2x minus 1. Then I have to solve for x. So I add 1. 2 equals 2x. Divide by 2. X equals 1. So my invariant point is at 1 and 1. That's one of them. So technically at 1 and 1 I would have a point. And then I plug in -1. -1 equals 2x minus 1. Add 1. Add 1. 0 equals 2x. Divide by 2. x equals 0. So my other coordinate is at 0 and -1. So it's here. How do I get the rest of the points on this graph so I can actually sketch it? Instead of just randomly doing that. Can I not just go to my calculator? So type in the rational into your calculator, not the reciprocal into your calculator. This one. Type that into y equals. I'm going to too. I just have to get my calculator shot. So in your calculator, you should have, if you have the old ones, you do 1 divided by 2x minus 1. You have to make sure you have the new denominator in brackets. If you have the new calculators, you can go alpha y equals enter. The only problem is if you use a fraction like this, it will give all your table values in fractions. So if you want to sketch, it's actually better to not use the fraction. It's better to use this one, 1 divided by. Because then at least your table values will be in decimals. Anyways, we want to be able to sketch this. So we can go second graph. And it will give us values. So I'm going to start at -3. -3 and -0.143. That's really close to the x-axis. We agree? So I'm going to go sketch it. -3 and -1 point whatever. So it's like here. What does -2 say? What's beside -2? It's really close as well. It's like -1, -2 point something. I don't remember. So -2 says -0.2. Right? Yes, no, maybe so. So it's close. It's still really close to that x-axis. Then -1 is -0.3333, so it's like a third, so it's like here. Now, if you look, 0 is at -1, and then what's happening is it's doing this, right? Now, what if I wanted to get 0.5? 0.5 is not on my calculator. How could I get 0.5? X equals 0.5. Second trace value. If I use second trace value, I can get any x with any y, correct? So now I go 0.5 and then enter, and what do I get? Looks like it errored me. Because it's so tiny, it's not even showing it to you. So what's happening here is this is getting like, it's curving and then it runs along here. Now put arrows at the ends. Now, I assumed that because I draw something, we know what assuming does, it's not good things. I assume that if I draw something in a certain way and put arrows on it, everyone else does as well. I also assume that if I draw asymptotes, everyone does that as well. Then it comes to the test and no one's drawing asymptotes and no one's putting on arrows, and then I realized you have to tell them. They don't just do what you do. That's what I realized. It took me a while. So, do you see how this is curving along here straight and I put an arrow? You're going to put an arrow because it's going to keep going. And do you see how this curves and comes down here and I have an arrow? You're going to put an arrow because it keeps going. Do you see how I have dashed lines? They're dashed and on here. That's an asymptote. Did I draw it? Yeah, you should draw it. People will literally not draw asymptotes even though I drew them the whole entire unit. And I'm blown away by that statement. So I now speak it. Okay? So at 0.5, I should have a dashed line with arrows. Why does it have arrows? What do arrows mean? Keeps going, continues, correct? And then here on my x-axis, I have a blue one, because that's my horizontal asymptote, and it keeps going, so I have arrows. Now I'm going to go back to my calculator, to my table of values. I have 1, 1. I have 2 and 0.33333, so it's like here. Then I have 3 and 0.2. And so this graph is curving, going up here for life, and then curving along here and going over here. So can we use our calculator to draw this? Yeah. Is it ever taken out of our hands? No. We're allowed the whole time. Okay? So I got my vertical asymptote for my non-permissible value. My horizontal asymptote is always y equals 0. The invariant points, you need y equals 1 and y equals negative 1. People shouldn't be on their phones. Y equals 1 and y equals negative 1, and then I can solve for them, and then I can go to my calculator to get other points, other coordinates. Do you agree? All right, you're trying this out. I'm giving you f of x equals 3x plus 1, and I want g of x equals 1 over f of x. I want a graph over here. I want a vertical asymptote. X equals, asymptotes are always vertical, because x equals lines are vertical lines. I want the horizontal asymptote. I want invariant points. And then we're going to talk about domain and range again, because we've done it before, but we'll do it again. So, here, we're going to do our vertical asymptotes based off of our non-permissible value. Here we would get 1 over 3x plus 1. So our NPV is going to be 3x plus 1 can't equal 0. Subtract 1. 3x can't equal negative 1. And then divide by 3, so we get x can't equal negative a third. And that's because it's a non-permissible value. Right? So it can't equal that, because if it did equal that, my denominator would be 0. So any x equals negative 1/3 will not be on the graph. Therefore, we call it a vertical asymptote. X equals negative 1/3. Because that's where the asymptote actually is, and that's where the graph is not. So the asymptote's there, but there can't be any graph there, because if it was, my denominator would be 0, and I'd have problems. So I go to x equals negative 1/3, and I try and draw a vertical line, even though my y is not vertical. That's a little bit of a bad drawing. Okay, so my graph can't exist there, and I put arrows on the end of it, and I put dashed lines, because the dashed lines mean the graph actually isn't there, correct? It's going to have to curve when it hits those. My horizontal asymptote for reciprocal graphs is always y equals 0. So I go to y equals 0, my not very well drawn horizontal line, and I put an asymptote on it. Then I go to do my invariant points. Invariant points will always be where y equals 1 and y equals negative 1. Because we learned when we drew them, that's what happens. They stay the same. And our original is f of x equals 3x plus 1. And if it's invariant between this and the reciprocal graph, it means it doesn't change, so we could use either equation to solve. This one's easier, so I always choose this one. So I get 1 equals 3x plus 1. Subtract 1. 0 equals 3x. Divide by 3. X equals 0. So I know my one invariant point is at 0 and 1. So I go to 0 and 1 and I make a dot. Then I go and find my other one. Negative 1 equals 3x plus 1. Subtract 1. Negative 2 equals 3x. Divide by 3. X equals negative 2/3. So my other coordinates at negative 2/3 and negative 1. So like here. How do I get more? I go to my table of values. So I go second table, and I get negative 4 and 0.9. So it's really, really close. Negative 3 and 0.125. Negative 2 and 0.2. Negative 1 and negative 0.5. Now, some people are stuck here and they're like, well, okay, that's great. At negative 2/3, I'm at 0, or at negative 1, sorry. So I could do something close to negative 2/3, or I could say, hey, it's curving and it's going to run along this part, that asymptote, and then this one's going to curve and run along this asymptote, all the way to the bottom. That should be a straight line. Mine is not. It should not be curving in. This is terrible. So it should be getting closer and closer to the asymptote, but not touching the asymptote. Okay? Then I go on the other side. I have 0 and 1. I have 1 and 0.25. 2 and 0.14. And these are just going to get really close. So this is going to curve and run along this asymptote. And not cross that asymptote. And this is going to curve and run along the x-axis, but not touch the x-axis. With an arrow. And then you have your rational graph. Now, domain and range are easy if you can get the asymptotes. Because domain, the graph exists everywhere on the left of this vertical asymptote, and the graph exists everywhere on the right to infinities, correct? The arrows are going out for forever. We agree? The only place that x doesn't exist is on the asymptote. And y, same thing. Y exists all completely above it and all completely below the horizontal asymptote, but not at it. So if you have the asymptotes, x equals negative 1/3, your domain is just, it can't equal that. And if your range is y equals 0, which it will be every single, or sorry, your horizontal asymptote is y equals 0, which it will be every single time, your range is just, it can't equal that. It can equal everything else. So how do we write that? So for our domain, we're going to go squiggly bracket because it means the set of x values such that x can't equal negative 1/3. And then this means but x is an element of the real. So that means x is everything else. So x can't equal negative 1/3 is the first thing we state, but x is everything else. That's what XER means. Our range is going to be y such that y can't equal 0, but y can equal everything else. Y is an element of the real. So if you have your asymptotes, you have your domain and range. Your asymptotes are equal to those values. Your domain and range are not equal to those values. All right? Is this making more sense, reciprocals? Making a bit more sense? Okay, good. Good talk. Isabel's like, no. Yes, it is. It's better than it was on Friday. I can tell because you actually did work. On Friday, you were like, no thanks. Not Friday, Thursday. You were like, mm-mm. So it's better. It may not be perfect, but a bit better. Okay, let's try one more equation where it's linear. So we're going to look at y equals x plus 3. And not y equals, sorry, I should say f of x. I'm going to change it up. I'm going to go g of x equals x plus 3, because I can label it any function letter, correct? And then I can say m of x equals 1 over what? What would I have to put on the bottom now?
G of x.
G of x. Because you guys get comfortable and then you can't adapt. That's how you are. It's like you always use f of x. You must now always use f of x. That's not how that works.
Like ABC for triangles.
Right. It's true. Creatures of habit. That's what you are. All right. So what am I going to want? I'm going to want a graph. Then I'm going to want a vertical asymptote. A horizontal asymptote. Don't know why I gave so much room for vertical. Invariant points. And then what did I add to the mix? What else did I want? Domain and range. Try it out. That was a big sigh. Oh, this one, we're going to get 1 over x plus 3. Then we say x plus 3 can't equal 0 because we have to find the non-permissible value. X can't equal negative 3. If it did, my denominator would be 0. So I have a horizontal asymptote at x equals negative 3. Dashed line with arrows. Okay, then my horizontal asymptote is always at y equals 0 every single time when it's a reciprocal function. When it's a rational function, this won't always be the case, but reciprocal functions, it'll always be y equals 0. So before I even go to do anything else, I'm going to do my domain and range. My domain is going to be x such that x can't equal -3, but it can equal everything else. And this one's going to be y such that y can't equal 0, but it can equal everything else. Now to get the invariant points, I want when y equals 1 and y equals -1. And my original was x plus 3. Oh, it wasn't f of x. And g of x equals x plus 3. So I can go 1 equals x plus 3, subtract 3, x equals -2. So I get, oh boy, it's getting -2 and 1. And then -1 equals x plus 3, subtract 3, x equals -4. Now with reciprocal linear functions, they're always in opposite quadrants. So if one's in quadrant 1, then this one's in quadrant 3, right? Like they're in opposite sides always. Then we need other points. So I go second graph, and I get -5 and -0.5, -6 and -0.333, -0.25. So it's just getting closer. Now, if I look here, -3 is where the problem's at. So if I go -4, I get a point. If I go second trace value -4.25, I'll get a y. It's at -0.8. So it's going to be somewhere. And then -4.25 is a little lower. So it just runs along here. And then runs along here. Okay? Then, this one, if I keep going, second trace, -2, 1, -1 and 0.5, -0 and 0.3, 0.25, 0.2. So this is going to run along the x-axis, just above it with an arrow, and then this is going to curve and run along here with an arrow. I have my graph. So that's if f of x is linear. What happens if f of x is a quadratic? Which is grade 11 at its finest. So, example, we're going to use f of x again. F of x equals x squared plus 3x minus 4. And then g of x equals 1 over f of x. So it's still a reciprocal, but it's a reciprocal of a quadratic. So it's going to be g of x equals 1 over x squared plus 3x minus 4. Now, my vertical asymptotes are my non-permissible values. What's the problem with this function currently? Can I get the non-permissible values when it's in the form x squared plus 3x minus 4? No, what am I going to have to do first? Factor. So what multiplies to me -4 now to give me 3, x plus 4, x minus 1. And I can go straight to brackets because it's product sum, because it has a 1 in front. What you looking for, Xander? What are you doing on paper? You looking for extra paper?
No, I'm good.
Okay. All right. So, we're not going to deal with a graph currently right now. We're just going to find vertical asymptotes and invariants, and then the next one we'll do a graph, and then the next one you're going to try. Okay? So let's talk about vertical asymptotes. This time it has asymptotes. Why? Not an asymptote. How many non-permissible values do I have? I have 2. these are not principal values because I have x plus 4 can't equal 0, but I also have x minus 1 can't equal 0. So I have x can't equal negative 4 and x can't equal negative or positive 1, sorry. So I'm going to have two vertical asymptotes, two dashed lines vertically at x equals negative 4 and 1. And we'll draw them in the next example. We're just doing this, just getting this set up first. Horizontal asymptote's really easy. Where's my horizontal asymptote at? Every single time when it's a reciprocal. Y equals 0. Hasn't changed. It's the greatest thing ever. You should be very happy with it. So it's the nicest thing. So my domain, same as before, I'm just going to have x can't equal a couple numbers instead of 1. My domain is going to be the set of, that's what this squiggly bracket means, x values such that x can't equal negative 4 and 1. XCR. And my range is y such that y can't equal 0, YER. Technically should be f of x, but we'll leave it be y's for now. Because your textbook has y's. Invariant points are harder when it's quadratic. When it's linear, you can just isolate x, correct? When it's a quadratic, you have to get everything to one side, side equal to 0, and factor or quadratic formula it every single time. So invariant points. This hasn't changed. My invariant points are when y equals 0 and y equals 1. That's a lie. I went to radicals of grade 12. It's where y equals 1 and y equals negative 1. And we still use our original. Our original is f of x equals x squared plus 3x minus 4. But now I'm going to get 1 equals x squared plus 3x minus 4. And I'm going to get negative 1 equals x squared plus 3x minus 4. And what's the issue with quadratics? You have to get everything to one side set equal to 0 and factor a quadratic formula every single time, correct? So this lesson couldn't be taught before quadratics. You would have to know quadratics first. So how do we solve this first one? Well, we'll have to subtract 1. So when you're asked a reciprocal invariant points of a quadratic function, it's way more work than when it's linear. And why? Because there's nothing that multiplies to give me negative 5 and that's to give me 3. Do you see that? So what am I going to have to use? The quadratic formula. Ted is staring it down right now. It's like burning laser beams into the quadratic formula of that thing. So this is my A. This is my B. This is my C. I'm going to get x equals negative 3 plus or minus. And I told you, if you're going to 30-1, this quadratic formula becomes your best friend because you use it a lot. So we need to know how to use it. Even 30-2, we use it. That's why it's on both 30-1 and 30-2 formula sheets, if you haven't noticed. So it's b squared minus 4 times a times c all over 2 times 1. So x equals negative 3 plus or minus 29. When you put that all in. Can 29 break down? 29 is a prime number, so it can't break down. So we actually get two solutions. We get negative 3 plus root 29 all over 2, comma 1. Negative 3 minus root 29 over 2, comma negative 1. Those are the two invariant points. If I want to sketch them, I'm going to have to turn those into decimals, correct? Or how the heck do you sketch that? So this one, we're going to add 1 over. I get 0 equals x squared plus 3x minus 3. Can I factor that? Anything multiply give you negative 3 and add to give you 3? No. So quadratic formula. So that's my A, B, my C. So we get x equals negative 3 plus or minus 3 squared minus 4 times A times C all over 2 times 1. X equals negative 3 plus or minus the square root of 12 plus 9 is 21 over 2. And 21 can't break down. There's no perfect squares in 21, like 4, 9, or 16. So we're going to get two solutions. One is going to be negative 3 plus root 21 all over 2. And negative 1, that's going to be one invariant point. And then negative 3 minus root 21 over 2. And negative 1. So I'm going to give you an example. F of x equals x squared plus 4x minus 5. And I want e of x equals 1 over f of x. And what are the things I'm going to want? Vertical aspect left. So.
Put it negative 1. Left side.
Ooh. Yeah. Tis true. I want the vertical asymptote, horizontal asymptote, domain, range, and invariant points, just like before. I don't want you to graph it. I don't care about graphing at this point. I just want those 4 things. So I want vertical and horizontal. I want the asymptotes, domain and range, and then y equals 1 and y equals negative 1 invariant points. Try it out. So we're going to get 1 over x squared plus 4x minus 5, which factors to 1 over x plus 5x minus 1. So my MPVs are going to be x can't equal negative 5 and 1. So I know my vertical asymptote. I should say, are going to be at x equals negative 5 and 1. And my horizontal asymptote should always be correct when it's a reciprocal because it's easy, it never changes. Horizontal asymptote is y equals 0 for reciprocals. My domain is just not equal to those. So it's going to be the set of, that's what squiggly bracket means, x values such that x can't equal negative 5 and 1, but x is down to the reals, everything else. And the range is going to be y such that y can't equal 0, but y is everything else. Y is down to the reals. Okay, my invariant points are when y equals 1 and y equals negative 1. And I can just use my original. So 1 equals x squared plus 4x minus 5. You could use the reciprocal, but honestly, there's no point because they get you the same, and the reciprocal is it seems more tricky. If you set that 1 over x squared plus 4x minus 5 to 1, that throws off so many people. So it's just easier to use the original because you're going to get the same point. Invariant means it doesn't change between the original and the reciprocal. It's the same point. So I'm going to subtract 1 over, and I'm going to get x squared plus 4x minus 6. And there's nothing that multiplies can be 6 and adds can be 4, so I have to use the quadratic formula. So I get x equals negative 4 plus or minus 4 squared minus 4 times 1 times negative 6 all over 2 times 1. So x equals negative 4 plus or minus 16 plus 24 is 30. What's 16 and 24? 40. And so we can break that down into 4 and 10. So we'll get 2 root 10 over 2. And then I told you if it can come out of the triangle, it can come out, correct? So we can take a 2 out of here. We get negative 2. 2 out of here and we get a 1. 2 out of here and we get a 1. If the 1 is in the denominator, do I need to keep it? No. So I get negative 2 plus or minus 1 root 10 or just root 10. My two coordinates are going to be negative 2 plus root 10 and 1, or negative 2 minus root 10 and 1. Okay. So we're going to get negative 1 equals x squared plus 4x minus 5. Add 1. 0 equals x squared plus 4x minus 4, which can't factor. So that's A, B, C. Sometimes they can factor. These ones haven't been able to. So negative 4 plus or minus 4 squared minus 4 times 1 times 4, negative 4, sorry, all over 2 times 1. X equals negative 4 plus or minus 16 plus 16 is 32. 32 can break down into 16 and 2. So we'll get 4 root 2 over 2. Take a 2 out. So we get x equals negative 2 plus or minus 2 root 2. So our invariant points are at negative 2 plus 2 root 2 and negative 1, and negative 2 minus 2 root 2 and negative 1. And your homework, I've sent some of this before. This one I'm checking tomorrow with my eyes. So it's just 4 of them. Because what you have to do is, on the same set of axes, label the asymptotes, the invariant points, and the intercepts. For me, I don't care about the intercepts. I want you to do exactly what we did up here. I want asymptotes, domain and range, invariant points. For tomorrow. I didn't give you a ton, so it's achievable. It's only 4. 2 linears, 2 quadratic.